Welcome to your next electricity lesson. I was like sat there for like 30 seconds trying to find the record the video button, couldn't find it. Anyway, here we are. Welcome back. Welcome to me and me. I mean, Mickey Talk today. So this is the next lesson in our mains electricity. It's actually the last teaching lesson I'll do in this topic. The next one's a revision lesson. And then the following lesson after that, I'm actually going to set some test questions to see what progress you've made on this topic. So this is the last teaching lesson in the topic. We're definitely going to want a calculator today. Obviously, you're welcome to use the calculator on your device or your laptop or whatever you have available, but you'll definitely be wanting a calculator for today's lesson. Okay, I'm going to go ahead and share my screen so we can get ourselves started. Let's have a look. Where's my share screen? Oh, it's been right slow today. And we'll get that up. We'll get the title of the lesson going. There we go. Oh, no share screen today. There it is, share screen. Good stuff. Right, there's my screen shared. There's the title of our lesson, which is Transformer Equations. You might recognize that transformer idea from the lesson we did previously about the national grid. So it's worth just looking back at what transformers were doing in the national grid. We said the national grid was all those cables and transformers that took the power from the power station along the cables to your house or the school or the factory that was going to use it. So the national grid is all those cables and transformers. And we said there were two sorts of transformer in the national grid, a step up transformer and a step down transformer. The step up transformer, well, its name is the clue, made the voltage of the power supply go up, and the step down transformer made the voltage of the power supply go down. Why do we want the really high voltage in these cables? Well, you want the high voltage so that you have a low current. And a nice low current means we don't lose very much energy from heat in the wires. Why do we want a step down transformer? To decrease the voltage so it's nice and safe in our homes. We have a 230 volt supply in our homes, which is less likely to give us a dangerous electric shock or start a fire. So the transformers are there to start the voltage, to change the voltage. So let's look at that in a little bit more detail. This square in the middle of the screen is a little sketch of a transformer. And you can see a transformer, just a nice big solid metal block. And there's some wire wrapped around one side. That's where the power comes in. And there's wire wrapped around the other side. And that's where the power goes out. So we're really sending the power from one side of the transformer to the other side of the transformer. We call the side that the power goes in the primary side of the transformer, and the side that the power goes out is the secondary side. So just like going from primary school to secondary school, the power goes from the primary side of the transformer or the secondary side of the transformer. Because there's wire wrapped around these sides of the transformer, you might hear some questions or some teachers talking about the power going from the primary coil to the secondary coil. So the coil of wire on the primary side to the coil of wire on the secondary side. But the important thing about the power going from one side, the primary, to the secondary side is the power stays the same on both sides. So if the power on this side is 1000 watts, then the power on this side will be 1000 watts. The power stays the same. And the reason we get exactly the same power on one side and this other side is because transformers are nearly 100% efficient. In other words, they don't waste any power going from one side to the other. So all the power that goes in the primary side ends up on the secondary side. Now we know from our equations that the way to work out power in electrical things is to multiply the current times the voltage. So for example, on this side, the power is 1000 watts. That might be because it came in at current 10 amps and voltage 100 volts. 10 times 100 equals 1000. When it goes over to the other side, don't forget that the transformer changes the voltage. Now, this is actually a transformer which is going to make the voltage go up. So let's say it makes the voltage go up to 200 volts. Now, the voltage has gone up to 200 volts, but remember I said that the power stays the same, 1000 watts. So to get the same power, I've got 200 volts times, what current? 200 times something gives me 1000. 200 times some mystery number gives me 1000. You can probably do that mental maths, or you can just divide both sides by 200, and that mystery number is 5. So you can see that on this side, I'm going to have a current of 5 amps. So on the primary side, I had current 10, voltage 100. On the primary side, I had current 5, voltage 200. Both sides give me a power of 1000 watts. The power was the same on both sides. But just like we said, the transformer has made the voltage go up, and that makes the current go down. Increasing the voltage decreases the current. So that transformer changed the voltage from 100 to 200. It changed the current from 10 to 5. That's a step up transformer, something which increases the voltage. So the sums you're going to have to do, just use this idea that the current times the voltage on the first side, the primary side of the transformer, always equals the current times the voltage on the secondary side of the transformer. So you might get a question which looks a little bit like this. Here we go. Here is a transformer. This transformer puts in its power supply at 0.2 amps and 100 volts. It comes out the other side at 0.1 amps, but what's the voltage? Well, I know that the current times the voltage on this side equals the current times the voltage on this side. So let's have a look. The current times the voltage on this side is 0.2 times 100. So that equals 20. The current on this side is 0.1 times a mystery number, but I know that equals 20. 0.1 times something equals 20. You might be able to do it mental maths, or we just divide both sides by 0.1, and my mystery number is 200. So 200 volts. So again, look, we can see that the power went into the transformer at 0.2 amps and 100 volts. It came out the other side at 0.1 amps and 200 volts. The transformer has made the voltage go up, but the current go down. Now, not all transformers are step-up transformers. Of course, we can have step-down transformers. So this transformer, for example, takes the power in at 0.1 amps and 2000 volts. It puts it out at 2 amps, but what's its voltage? Well, we just use our same idea. The current times the voltage on the primary side equals the current times the voltage on the secondary side. So let's have a look. Here on this side, the current is 0.1, the voltage is 2000, so that gives me 200 on this side. On this side, my current is 2, and my voltage is a bit of a mystery, but I know that equals 200 because the power has to be the same. So 2 times a mystery number equals 200. Divide both sides by 2, my mystery number is 100. So that's at 100 volts. So in this example, I've got a step down transformer. The voltage went from 2000 to 100, it went down. But the current went from 0.1 to 2, it went up. So that's an example of a step down transformer. But for all these transformers, it's the same idea. It's the idea that if you multiply the current and the voltage on the primary side, you get the same answer as the current times the voltage on the secondary side. And that gives us our transformer equation. Because transformers are nearly 100% efficient, the input power should always equal the output power. In other words, the voltage times the current on the primary side, that's what the little letter P stands for, should equal the voltage times the current on the secondary side. That's what the little S stands for. That equation looks complicated, but all it's really saying is voltage times current on one side equals voltage times current on the other side. Vp times Ip equals Vs times Is. Voltage on the primary times the current on the primary equals voltage on the secondary times current on the secondary. This is not a learning equation. You will be given this equation on the formula sheet if you need to use it. So there are two worksheets attached to this lesson. There are some transformer equations for you to try, and then which I'm going to talk through with you. But then I am going to give you another worksheet called More Transformer Equations, which you are to do independently and send to me so I can mark it. So if you want to make sure you've got the first transformer equation question sheet open, so it's not the one called More Transformer Equations. So let's go. Let's work through the first three of these together, and I expect you to fill in these worksheets either online or on paper or in your books, so I can see that you're following these calculations. You're going to submit this work to me, and you're going to submit both worksheets to me. Let's have a look. The first question on the worksheet says a transformer in the national grid has a potential difference of 10,000 volts in its primary coil at a current of 60 amps. If the potential difference in the secondary coil is 300,000 volts, what is the current in the secondary coil? Okay, let me get my sketch pad up. So I know that voltage in the primary, I better just get that into a pen. So let's give myself a nice black, I'll give myself a slightly chunkier pen, I think, so you can see my writing. There we go. So primary voltage times primary current equals secondary voltage times secondary current. Let's have a look. Now, first of all, they're using the word potential difference here instead of voltage. That's fine. So I'm going to fill in the numbers I know here. Primary voltage, that's 10,000, times primary current, that's 60, equals secondary voltage, 300,000, times secondary current. Well, I don't know that. That's my mystery number. So 10,000 times 60 equals 300,000 times my mystery number, my secondary current. So let's have a look. I'll work these out. 10,000 times 60 is 600,000 equals 300,000 times my secondary current. So to find my secondary current, I divide both sides by 300,000, and that gives me my secondary current is 2 amps. So divided both sides to get that, and let's check my answer to see if I was right. Oh, come on, Mr. Bremner. Yay, good for me. 2 amps was the correct answer, but it is important you show you're working out for those. So make sure you fill that in on the worksheet. Let's have a look at question 2. What potential difference will be at the secondary coil of a transformer if the potential difference in the primary coil is 1,550 volts and the current in the primary coil is 8 amps? The current in the secondary coil is 16 amps. Flipping heck, it's a lot of words there, but really I'm just going to fill in the three numbers into my equation. The primary voltage times the primary current equals the secondary voltage times the secondary current. Just going to find three of these numbers. Let's have a look. My primary voltage, let's have a look. The primary coil is 1,550 volts times my primary current. There it is there. Current in the primary coil is 8. The secondary voltage, that's the one I'm looking for. That's my mystery number. Times the secondary current is 16 amps. There you go. Oh, I don't need to write A for amps. That's a bit of extra work there. So that's my sum. 1,550 times 8 equals my mystery number times 16. So I can just work this out now. 1,550 times 8. I'm just going to grab my calculator to do that. 1,550, 1,550 times 8 gives me, let's have a look, 12,400. 12,400 equals my mystery number times 16. So to find my mystery number, I'm just going to divide both sides by 16. Divide by 16 equals 775. So my secondary volts was 775 volts. Back to my worksheet. Back to my worksheet, 775 volts. Awesomeness. Third one on this worksheet. Let's have a look. The built-in transformer, I'm just going to get my sketch pad up here. The built-in transformer for a tablet plugs into the mains, so it has an input potential difference of 230 volts. The label on the transformer says that its output potential difference is 5 volts and its output current is 2000 milliamps. Calculate the input current to the transformer if it's 100% efficient. A lot of words again for really just finding three numbers. My primary voltage times my primary current equals my secondary voltage times my secondary current. Okay, let's just find me three numbers here. My primary voltage, there you go. Input potential difference, 230. So 230 times my primary current is my mystery number, equals my secondary potential difference. There it is. Secondary potential difference is 5 times my secondary current. Oh, now then, just spotted there. That's in milliamps. So 2000 milliamps. So I need to divide by 1,000. So I'm actually getting 2 amps there. That was sneaky. That was 2 amps. Okay. That was an extra mark to be picked up there. So 230 times the primary current equals 5 times 2. I can just solve this now. 230 times the primary current equals 10. So I'm just going to find the primary current by dividing both sides by 10. So my primary current equals 2.3 amps. But it does say give your answer to one significant figure. So my one significant figure would just be, that's what first significant figure is, just 2 amps. So there you go. That's how we use our transformers equation to solve these questions. So you should have that worksheet completely filled in with your workings, and you could submit that to me. And then your final job is to try the second more transformer calculations worksheet that's attached to this lesson. So I need that submitted to me as well with your calculations and answers so I can mark those two. Please drop me a message in the chat here on Google Classroom if you need any help with those, and I'll go through the answers to those at the start of the next lesson so you can be ready to mark them then. Good luck. Thank you very much. I'll end my video now.